last part of today's fundamental section. So the last speaker of today is Hyungryul back from KAIST. We'll talk about bifoliation of the planes and the flows.
All right, thank you very much. Thank you for coming and the great conference. Are you all enjoying Korean afternoon? It seems all the speakers today afternoon is Korean, so I'm gonna finish with Korean afternoon. So I'm at KAIST, so I'm local. So if you have any questions, math or otherwise, let me know. So today I'm going to talk about the bifoliations on the plane and the flows in three-manifold. So here, the bifoliation means you have two foliations in the plane. I'll talk about the definition in a minute. So as a motivation, so motivation for the whole theory in this direction is the so-called Thurston's universal circle theorem. So the setup is if you have a three-manifold with compact toroidal, so toroidal here means it doesn't have any embedded torus with pi1 injectively embedded pi1 torus. And F here is a co-orientable top foliation. So here, whenever I say a foliation in three-manifold without talking about dimension, I mean two-dimensional foliation by two-dimensional submanifold. Here the top, the definition is there exists some closed loop in the three-manifold which is transverse to the foliation, and it meets every leaf of the foliation at least once. So you have the three-manifold obtained as a union of two-dimensional things. There is some one-dimensional loop traveling within the three-manifold. It is always transfers to this foliation, but it meets every leaf at least once. Okay. So here's the typical the picture I use as an example. It's not a typical top foliation, a very special case, but it's easy to understand. So if you have any surface, it's a sigma G, it's a close orientable surface of genus G, and here, all right, yeah. So the F is some homeomorphic orientation preserving homeomorphism from sigma G to itself. So if you consider sigma G cross I, the surface is thickened with as a product with a closed interval. You have two boundary components, both homeomorphic to sigma G. Now I have a homeomorphism on sigma G to itself, so I use it to glue this two boundary component to form a three-manifold without boundary. So that's construction written here is called the mapping torus. The closed three-manifold, which has a cross section, which is always a copy of the sigma G. And if you just consider the loop transfer traveling this mapping torus around once, then you can get a witness for this foliation to be topped. Okay. All right, so that's the setup. So to state Thurston's theorem, we need two general theorems about foliations. So one theorem is Palmeira's theorem. So if you have a three-manifold with top foliation, co-orientable top foliation F, and here M tilde is a universal cover of M, and the F tilde is a pullback of F. So this is the foliation where when you go to M via the covering map, this covers this foliation M. Then there exists a one-dimensional foliation, the foliation by lines of R2, non-fancy F, such that your universal cover is, first of all, topologically homeomorphic to R3. But not only that, the foliation in the universal cover is just a product foliation. Because R2 has a one-dimensional foliation, you just consider the product with R. So each one-dimensional leaf in this capital F will become, by taking a product with R, become a two-dimensional thing, R2, right? Copy of R2. So that's the picture. So in fact, Palmeire's theorem is not really about dimension 3. It works actually in dimension 3 or higher. So in any dimension, if you have a topolation, you have, if it is n-manifold, then in the universal cover, you have a foliation in Rn-1, and the foliation in the universal cover is just a product foliation. So that's one theorem. So the upshot of this is, first of all, the universal cover is always homeomorphic to R3, and each leaf of the lifted foliation F tilde is homeomorphic to R2. Okay? That's the conclusion we want to take from this Palmeira theorem. Any questions so far?
It's like spherical as well.
That's actually a great point. I should have said that the M is right, not or doesn't have S2 cross S1 as a finite shaded cover. Yeah, that's one of the underlying assumptions. Thank you very much. Yes. Oh, so this word means that there is no embedded torus. The embedding is injection on the pi1 level. All right, so that's one theorem. And the second theorem is Kendall theorem. So that's a sort of the simultaneous uniformization theorem for these two-dimensional foliations. So in this setup, if you have a aspherical atorial compact free manifold, F is core-interval topolation again. So you have a Riemannian metric on M such that its restriction to each leaf of the foliation is a hyperbolic metric. So it's not a hyperbolic metric on M, but it's a leaf-wise hyperbolic metric. Okay? Though, if you are free manifold people, actually, you may wonder like something about what the Riemannian metric here. So it's a smooth metric in the leaf direction, but tangentially it's only continuous metric actually. You don't know where it's smooth in the transverse direction. So anyway, so that's a leaf-wise hyperbolic metric. So by combining with the Palmeira theorem, the conclusion we want to take is that in this setup, the universal cover of M is R3, and with respect to this leaf-wise hyperbolic metric, all the leaves in the universal cover can be considered as a copy of hyperbolic plane, right? So you know that as topologically it's a plane, and using this metric, it's a hyperbolic metric. So each leaf now is considered as a hyperbolic plane. So from that, we know that each leaf of F tilde has a circular infinity, the ideal boundary of the hyperbolic plane. So now I'm going to use L to denote the leaf space of F tilde. So this means you just take a portion of the space by portioning all the leaves to a point. So collapse every leaf to a point, the space of leaves, okay? Space of leaves of this foliation. Right. So this is going to be useful for later on as well. So I'm going to talk about the topology of the leaf space of F tilde a little bit. So let's visualize this in dimension 2 because that's easier. So in R2, if I consider, first of all, I use this straight line colored in red, and the left half plane, I foliated it using parallel copies of the straight lines, all colored in red. And here I draw a blue straight line, vertical one. Again, on this half plane here, I foliated with the parallel copies of straight lines colored in blue. Now I have this infinite strip in between. And then I foliated using these curves. So this is also topologically just the infinite line. but the both end goes to all the way to infinity here. It's asymptotic to the one end is asymptotic to this red line, and the other end is asymptotic to this blue line. And I collect infinitely many of them to foliate this infinite strip. So what is the leaf space of this question? What is the leaf space of this? So if you think about it, so this part here gives you a infinite ray, and where this red dot corresponds to the boundary leaf here. And in this part, we also have another infinite ray. This blue dot corresponds to this blue line here. And in here, you have infinite line corresponding to this purple leaves. And the point is, these 2 points, red and blue, are not separated by open set in the leaf space. Because if you take any open neighborhood of red and open neighborhood of blue, that contains infinitely many purple lines in common. So the neighborhood of this guy will be some sort of an open interval which contain red dot as in the interior. And open neighborhood of this guy is some open interval which has the blue point as in the interior, but both of them will contain infinitely many points in the purple part. So in general, the leaf space is this is the expression Thurston used. I'm going to just use it here. So it's a non-Hausdorff one manifold. In the one manifold, in the sense that every point has a neighborhood homeomorphic to open interval in R, but not necessarily Hausdorff because of this behavior here. So here is the statement of Thurston's theorem. Well, part of the statement. So in this setup, you have an injective group homomorphism from the fundamental group of M into homeomorphism, orientation preserving homeomorphisms of the circle. So here I wrote univ as indicating that this is something about the universal circle, but just ignore it. You have a group injective group homomorphism from pi1 to the group of homeomorphisms of S1. So that means you have a faithful action of fundamental group on S1 by orientation preserving homeomorphisms. Not only that, if you take arbitrary element in fundamental group and arbitrary leaf of the lifted foliation in the universal cover, then here you have this commutative diagram. So what is this map? So this map is a map from circle to circle. There's a continuous surge action such that every point in the range, the preimage is connected. Okay. So it's just a map such that some closed intervals are collapsed to point. So you do have such a map for every leaf in the lifted foliation. First of all, recall that Palmera plus Kendall says that this leaf is considered as a hyperbolic plane. So this S1 infinity alpha is the ideal boundary of that leaf alpha, okay, when you consider it as a hyperbolic plane. And now this is a monotone map, the map I described, circle to circle. So you have this for every leaf in F tilde. And now the row of G act on the S univ. So there is this action, this G via this action row. And here G, this is just a deck transformation action. So since F tilde descends to F in M, so deck transformation, of course, maps leaves of F tilde to leaves of F tilde, right? So the alpha will be mapped to some other leaf of the foliation. Let's call it G alpha. So for G alpha also, you have the circle infinity, and there's this monotone map from the universal circle to this circle infinity. And the Thurston theorem says that this diagram always commutes. The fourth, in some sense, this action of pi1 on the universal cover, when you see this action at these circles at infinity, it's always semi-conjugate to the single action on a single circle. But that's what universal circle is. and it's called the universal circle for co-orientable top foliation. And another data obtained in Thurston's work is that this action has a transverse pair of dense invariant laminations. So I'll explain the word here in a minute, but somehow not only this is a very nice action on the circle, which captures the pi1 action on the from the perspective of the foliation, but also this has some invariant structure, which I want to focus on today. So to explain what it is, let's get to the basics. So the definition of circle laminations. This is, first of all, a subset of this guy. So this is what S1 cross S1 minus the diagonal. So the set of pairs of two distinct points and quotiented by the involution. So I don't care about the order. So unordered pairs of points on the circle. And this is called a lamination if satisfying these two conditions. One is closed as a subset of this guy. And no two elements are linked. So this is an example. So red pair and blue pair and the pink pair are this form of circle lamination. And what do I mean by linked? First of all, if your pair is linked as in this picture, so if you just identify your circle with a boundary of an open disk, well, you can draw a chord, and if they actually intersect in the interior, then we call it a linked pair. And if they are, if you can draw a chord which are disjoint, then which we call unlinked. Now, one more case to consider is that these two pairs actually share one point. In this case, still unlinked. If you draw two chords, they intersect on the boundary, but not in the interior of the disk. In this case, we still call it unlinked. Okay? So if you collect only these pairs point which form a closed subset in the space of all unordered pairs, the point of the circle, we call it a circle lamination. And why the lamination? Because it actually has a geometric realization. So if you identify your circle with the ideal boundary of H2, and just draw for each element in your lamination, just to draw a by infinite geodesic, which has that 2 point as the end at ideal boundary, then you get a geodesic lamination of H2. So this is a union of by infinite geodesics of H2, pairwise disjoint, and it forms a closed subset of the hyperbolic plane. So it's a geodesic lamination. So that's of course, depending on your identification, you see something different, but up to homeomorphism, orientation preserving homeomorphism, the picture is well defined. So I'll call it a geometric realization of circle lamination. So for this reason, this set of point or set of pairs of points is called a lamination. Any questions? All right. So for a circle lamination, the end of lambda is defined to be the set of points on the circle such that it is an end of some leaf of the lamination, right? So if there are some other point Q in the circle so that this pair PQ is an element of lambda. And lambda is called dense if the set of end is dense in S1 as a subset of S1. So if you think about it, the lambda being closed in this space of unordered pairs of points does not imply the closedness of the end space as a subset of S1. So it has nothing to do with that. And two pairs of circle laminations is called transverse if they are disjoint. There's no common element. All right, so that's the word in this Thurston theorem, a transverse pair of dense invariant laminations. There is a transverse pair of laminations, each of which is dense, and both are preserved under the group action. Okay. So you have this invariant pair of laminations in the case of the top foliations. Disjoint. No common leaf. Yeah. All right, so among those laminations, there's particularly useful laminations. This is a class of laminations called very full laminations. So the lambda is very full if its geometric realization has only ideal polygon gaps. So whenever I say ideal polygon, I mean the ones with only finitely many sides. So like ideal triangle, ideal quadrilateral, ideal pentagon, things like that. So this is one example. So the Fairy tessellation of hyperbolic plane is a collection of geodesics so that it decomposed the hyperbolic plane into ideal triangles. Right? So this is an example of a very full lamination. And the connected component of the complement of the lamination or geometric realization of the lamination is called a gap. Okay? So in other words, lambda is called very full if all the gaps in the geometric realization are finite-sided ideal polygons. So where are those laminations? The one big source of examples is surface. So if you have any hyperbolic, closed orientable hyperbolic surface of genus G, and say if this is, in this case, the picture I drew is a genus 3 case. So in this case, it can be decomposed by some collection of closed geodesics into 2G minus 2 pairs of pant. So here a pair of pant means topologically a three-punctured sphere with geodesic boundary. Okay? And once you have a pair of pant, then this can be actually decomposed into two ideal triangles. For each pair of boundary component, you can find a bi-infinite geodesic on the surface so that each end accumulates spiral tooled to one of the boundary components. So if you do this for each pair boundary component, you have three bi-infinite geodesics which cut this pant into two ideal triangles. So if you do this, then each surface now decomposed into 4G minus 4 ideal triangles. When you lift it to the universal cover, the lift of this geodesic lamination, of course, it only has ideal triangle in the gap. Right? So it is an example of a very full lamination. And also, since you can do this with infinitely many different set of curves which cut the surface into pairs of pant, you actually do have a lot of different very full laminations in the on the hyperbolic surface. So when you lift this very full geodesic lamination to the universal cover, the pi1 of the surface act as a deck transformations on the hyperbolic plane, which preserve this geodesic lamination you constructed from the surface downstairs, right? So if you look at the setup end of this geodesic lamination, it's preserved under this. So the pi1 of sigma g action on H2 by isometries extend continuously as action by homeomorphism and ideal boundary. And that action actually preserves this circle lamination, which is obtained as the endpoint of this geodesic lamination. So you do have an example or have many examples of groups which act on the circle with many very full invariant laminations. The one natural question is, well, are these only examples? And actually, yes. So if you have so this is stemmed out of my work and finished in the collaboration with my former student Kyung-no Kim. So if you have a group of homeomorphisms of S1, let's just assume it's torsion-free and discrete. And so here discrete means as a discrete subspace of this guy, which is now considered as equipped with a compact open topology. And G admit very full invariant laminations lambda 1, 2, 3, three of them, such that the end space are disjoint. If and only if G is the fundamental group of a hyperbolic surface where this hyperbolic surface has no cusps. So it doesn't matter whether this is a surface of infinite type or has an ideal boundary or whatsoever, as long as it's a hyperbolic surface with no cusp, then this is always achievable as a group with these conditions. And there's also a version of this theorem which includes the surfaces with cusp. The way how you do it is you just erase the where part, and they modify this condition here so that the intersection between the set of ends of lambda 1, lambda I, and lambda j is always exactly the set of points which are fixed by parabolic element in the fundamental group. Here, parabolic is the homeomorphism which has only one fixed point on the circle. Then those will actually do correspond after quotient the cusp of the surface. But anyway, so that's a surface version of the theorem. So somehow, if you know you have a group action on the circle with enough invariant laminations, that's a rigid information enough to conclude something about the group. In this case, you can conclude this group is actually a surface group. All right, but there are many other examples with two invariant laminations. So the theorem is about if you have three variable invariant laminations, then it's automatically a surface group. And if you have only two of them, but it's not enough to guarantee it's a surface group, but also there are actually counter examples to that. So first of all, if you have a setting of co-orientable top foliation, the Thurston theorem says that you have an action in the universal circle with the two invariant laminations. That was the theorem I stated before. And, although these are not very full laminations. Okay? But anyway, so having two laminations, that's an example. Another example is the mapping torus case. So if you have Fourier manifold obtained as in the example I gave you, so surface torus interval gluing using the surface homeomorphism, then this also has an action on S1 and has a pair of laminations invariant. In this case, they actually do come from the stable and unstable lamination for the monodromy map. So if you know the pseudo and Anosov homeomorphisms, if you don't, you don't have to for this purpose of the top. But there is actually, this is the case when these pair of laminations are very full. Of course, you can think of this theorem as a special case of number one, right? Because this gives you the top foliation. I used this as an example of top foliation, right? But on the other hand, I just wanted to emphasize that this particular class of examples, you do have a variable, two variable invariant laminations without group being a surface group. Okay. So this is not just very full, but also each lamination, stable and unstable lamination is satisfying some condition I called loose. So this is the picture definition of loose, actually non-loose. So lamination is called non-loose if you have some two gaps which share a vertex. Loose means not non-loose. Okay? So if you don't see any picture like this, so any two gaps are not only disjoint in the interior of the disk, but also on the ideal boundary, then the lamination is called loose. Okay, so another source of examples is the more recent one. So there's a series of papers by Saul Schleimer and Henry Segerman thinking about so-called Viering triangulations of non-compact Fourier manifold. In this situation, I'm not going to define what Viering triangulation is in this talk, but if you have such a nice class of triangulations, this is an ideal triangulation, by the way. In this case, you also have a way to construct a faithful action on S1 by the fundamental group, which they call Viering circle, because the circle constructed from the structure of the Viering triangulation. And it also has a pair of invariant lamination. And here, these lamination, also each of them is loose in the sense I just defined, but all gaps are crowns. So I'm gonna define what crowns are. But before that, first of all, I'm gonna just first make a remark. So once you have a Viering triangulation, the Viering structure, what it gives you is that the two skeleton of this ideal triangulation is what is so-called the Brented surface. So if you know the train track, that's a two-dimensional version of train track. So it's a two-dimensional simplex where every edge has a well-defined tangent direction. Okay. And once you have a Burin triangulation, this is just a simple argument which you can show that there is always a top foliation carried by the true skeleton of the triangulation. So in this case, you do have Burin circle coming from Burin triangulation by the work of Schleimer and Schegerman, and also this top foliation gives you the universal circle using the work of Thurston. And recently, the Laundrie, Minsky, and Taylor said that this Burin circle can be actually considered as a universal circle of the top foliation. I said can be considered because universal circle is actually not unique. Any faithful action of fundamental group of M on S1 satisfying the data described in the Thurston theorem is called the universal circle. And even up to semi-conjugacy of the actions is not unique. So it's just saying that this Burin circle action actually do satisfy all the conditions which are supposed to be satisfied by the universal circle action of the top foliation. Anyway, so that was just a remark. So this is a crown. The crown is a gap where it has an infinitely many sides, only countably infinite, and the vertices accumulate to a single point from both sides, and which we call a pivot point, the crown. So this is a crown gap. So what I just said is that, well, here, if you have a mapping torus, then you have an action of fundamental group on S1 with pair of very full loose laminations, where it means that the loose and every gap is a finite-sided ideal polygon. In the Burin circle case, you do have the similar situation. Each of them is loose, but all the gaps are crowns. So I'm going to define a lamination to be quite full if it is one of these two types. So all the gaps are either ideal polygons or crowns. Okay, so the mapping torus and the Burin triangulation cases are two extreme examples. Either only has ideal polygons or has only crowns. Okay, I'm going to say quite full if the mixed of these two. So here is a definition of Burin pair of laminations. So if you have two laminations such that each lambda I is quite full and loose, and then transfers, not just having this is called actually strongly transferred, not just disjoint, but also ends are disjoint. This is stronger, right? And the gaps of lambda 1 and lambda 2 come in pairs in the sense as in this picture. So if blue is arbitrary gap in lambda 1, there is some red gap in lambda 2 such that, well, it is the same type. If blue gap was an ideal polygon, then the red gap should be also ideal polygon with the same number of vertices, and the vertices appear in alternating way on the circle. If blue one was a crown, then red one is also a crown. Again, the same. The vertices should appear in an alternating way on the circle, and they necessarily have the same pivot point. So if that always happens, then we say the gaps of lambda 1 come in pairs, and also sometimes it's called interleaving. It is two gaps interleave. So if these conditions are satisfied, and this pair of laminations is a Burin pair. So again, mapping torus or the frame manifold with Burin triangulation is an example of gives the example of a group acting on the circle with a Burin pair of laminations invariant. So that's what I just said. So these two are two examples of Burin pair of laminations. So I actually don't have a concrete example of a Burin, the situation where you have a three manifold group acting on the circle with Burin pair of laminations where both ideal polygon and the crown actually do appear. I don't have a way to concretely construct such an example. That would be interesting. But anyway, so here's the result of myself with Hongtaek and Kyung-no. So if you have a group acting on the circle by orientation preserving homeomorphisms, if it preserves a Burin pair of laminations, then it's always a three manifold group. Okay, so I'm gonna say three manifold, but to be a manifold group, you need to actually have a torsion free. If you have torsions, you have a three orbifold fundamental group. But anyway, so let's just simplify our life. Let's just assume every group is torsion free for this talk. That is a three manifold. So to sketch where this three manifold comes from, so here is the sort of picture of a geometric realization of this varying pair. So I drew only two interleaving pair of ideal polygons, but you imagine this is actually full of this picture on the disk. And you can go from here to, again, a plane by appropriate collapsing. So here, I'm not going to define exactly what equivalence relation I'm using to take the quotient, but all this sort of the gap, the connected component. If you see the connected component of the complement of the union of these two laminations, and imagine you collapse to a point. Well, you need to be careful, but that's sort of the idea. So the interleaving pair of polygons will actually, after collapsing. So first of all, what you need to show at the very beginning is the image of leaves is a real line. And the interleaving pair will give you a pair of singular leaves, which has a shared prong singularity. So after careful collapsing, what you get is the quotient still homeomorphic to a plane with a pair of transverse singular foliations, where the singularities are prong singularities coming from the interleaving pair of polygons. Now, in this picture, there's one. Well, actually, I'll tell you. Actually, there are two ways to go from here. But the one way we did in the work with Hongtaek and Kyungno is first remove the singularities, so you get a plane with many punctures, but now transverse regular foliations, and you go to the universal cover. The universal cover is going to be R2 with the transverse regular foliations in this case. And this is a bifoliated plane. So the plane with bifoliation, transverse pair of regular foliations, and satisfying certain axioms and then the set of axioms was given in this Schleimer and Segerman's work. And this kind of bifoliated planes are called Lume spaces in their paper. So we show that this universal cover, after removing singularities here, is actually a Lume space in the sense of Schleimer and Segerman. And what is a good thing about Lume space is that in this case, the Schleimer and Segerman gave a way to construct R3 with varying triangulation coming from this Lume space. Some certain set of bifoliated plane, there is a recipe to construct R3 with varying triangulation. And this construction is functorial in the sense that, well, if you have a nice action of a group here, then you also do have a nice action of a group here, which act as a cellular automorphism of this varying triangulation. So let's call D to be the deck group for this covering, universal cover. And D will act on here as a deck group by this functoriality proven in Schleimer and Segerman. So you quotient it out, you get a three manifold. This is a schematic picture. We don't know exactly what it looks like, but it kind of looks like a R3 with many tunnels removed. So so far, there's nothing. This picture has nothing to do with the group. If you have a pair of varying pair of laminations on the circle, then you can always get to this three manifold. But now, if you consider a group G acting on the circle, preserving this guy, well, by taking a quotient, you do have an induced action of G here, but you don't have an induced action here. You cannot go to the covering, right? Sometimes you can, but it's not always possible. But on the other hand, you do have a group action here. That's this functoriality business gives you doing. So the G action on this guy gives you G action here. And we show that this action is properly discontinuous and free. And the stabilizer of this boundary annulus is either Z or Z2. So you can actually extend your action by filling in these cylinders by putting the solid cylinder in, and extend your group action so that still the action is free and properly discontinuous. And show that, well, then now you have a nice action on simply connected Ray manifold, and taking a quotient of the Ray manifold by G action, you get the some Ray manifold which has G as a fundamental group. So this last step is necessary because, I mean, you can take a quotient of whatever you have, but this is not simply connected to begin with. It doesn't give you the fundamental to be G. So that's sort of the sketch of the construction. And more recently, now I'm thinking about the flows in Fourier manifold, which I'll talk about in a minute. And from that perspective, actually, I don't actually have to go through the loom space all the way. That's the sort of content of the last 9 minutes. So not necessarily, because I'm not assuming anything about the group other than acting on the G. So it's whatever. But if M is compact, then it's always hyperbolic. But under just the assumption of having G acting on the circle with pair of laminations doesn't necessarily right away give you a compact manifold. Okay. So here is some sort of a loom space business. I'm gonna first skip it to sort of go to the other part of the theory a little bit. So by the way, this is also considered as a bifoliated plane in the sense that, so this is a bifoliated plane where the bifoliation are regular, it's regular, but people actually consider a plane with a transverse pair of singular foliations where singularities are prong singularities, isolated prong singularities, as a bifoliated plane as well. So this, in a more broader context, this is also a perfectly good bifoliated plane. So how many people know what Anosov flow is in Fourier manifold? Okay, how many people don't know what Anosov flow in Fourier manifold? I saw some hand before. All right, so I have 2 examples, but for the time sake, I'll go through only one example very quickly. So if you consider the mapping class group of the 2 torus, where the mapping class group here means it's a group of orientation preserving homeomorphisms up to homotopy, it's actually isomorphic to SL2Z. So when you consider T2 as a quotient of R2 by Z2, then, well, any mapping class, when you lift it to R2, well, it should preserve the Z2 and also preserve the area. And now you just do the homotopy, and you can always homotopy to the linear map. Okay? So that's how you get this SL2Z. So if you pick an element in SL2Z, it's a 2x2 matrix with integer coefficient. And the characteristic polynomial, you write it like this. So the discriminant of this guy is A plus D 4 minus 4. What is A plus D? That's a trace of this 2x2 matrix. So when the trace of A is bigger than 2, then it has 2 eigenvalues. Okay? Let's call them lambda and 1 over lambda. In this case, the corresponding mapping class is called Anosov map of T2. So why do we care about this situation? Because you have 2 eigenvalues and consider the eigendirection for each eigenvalue. So there are 2 directions. And you consider the linear foliation of R2 along these 2 eigendirections. So one of them is F lambda and the other one is F1 over lambda. And now what happens to here if you consider the when you go to the mapping torus of this Anosov map. So you consider the T2 cross-I and glue the boundary component together using this corresponding mapping class of the two torus. And we can always consider a suspension flow in the mapping torus picture. So you have a surface cross interverse, so you have this one-dimensional foliation in this product. And when you glue this two boundary component, this one-dimensional foliation continue. Right? And you just consider it as a flow, flowing from one surface to another in time one or something like that. So that gives you the suspension flow. And this picture is actually, if you go to the universal cover of this mapping torus, in the universal cover, there's a lifted flow, which descend to this suspension flow in the quotient. And this can be seen as the space of flow lines in the universal cover. It's kind of a cross section, right? So that's a universal cover of the two torus. So the universal cover of this guy was going to be R3, but if you look at this, the cross section, that the plane transfers to these flow lines, lifted flow lines. That's this picture, and you have this two one-dimensional foliations. And when you go to this universal cover, so if you flow along the flow line, then these two actually, what is this flow line? Flow line is the intersection between one of this blue line cross R and the red line cross R. So it's actually an intersection of this a pair of leaf of two-dimensional foliations in the universal cover of the mapping torus. And when you flow, then in the blue plane, the other flow lines, blue plane. Yeah, the other flow lines looks like getting closer and closer to your flow line. And in the red plane, the other flow lines looks like they're getting farther and farther away from your flow line. That's the Anosov flow. So whenever you have an Anosov flow, then you have this picture as a space of flow lines. The space of flow lines is always homeomorphic to R2. And not only that, if you actually consider the topological end of these leaves of two foliations, they have a natural cyclic order preserved by the fundamental group of your manifold. So you can actually consider a circle containing those set of ends and collapse all the gaps you see, and you get a sum action of fundamental group on the circle. So whenever you have an Anosov flow in Dream manifold, then you do have this picture which gives you a circle, the fundamental group action on the circle. And also this actually does have a fun action on the bifoliated plane. Right? So I underestimated what I prepared. So one thing I just want to emphasize is that unlike the usual picture we saw in circle laminations, now we have to give up something. So if this is a one foliation in one of these foliation, in your bifoliation coming from Anosov flow, then if you consider its geometric realization, so you just consider only the end pair of point in the circle and take it to H2 and make a geometric realization. If you know what pulling type means, this is pulling type, right? You actually do see that there is a sequence of blue, purple leaves converging to this particular geodesic, but that should not be in the picture. Because the blue guys and the purple guys actually converge to the blue, red, and green in the original picture. So this leaf is not part of your picture if you want to have some sort of lamination model for this foliage. So now you have to give up the closeness. You have to say, well, I'm going to consider set of pairs of points in the circle, not necessarily closed, but still a pairwise unlinked. So what happens is that actually, if you have Anosov flow, or if you even know what it is, pseudo Anosov flows, then the picture you get is some sort of picture like this. So it's always something obtained from quite full lamination by removing at most one side from each gap. That's the worst thing can happen. So in the recent paper, the Barthelmé-Bonatti-Mann, they gave a necessary and sufficient condition for a bifoliated plane to correspond to the picture in the orbit space epsilon also flow. And what we gave is these, the last maybe the yep. So the okay, so that's the last theorem. So if you have a group action on the bifoliated plane satisfying some axioms, which is some subset of the axioms which are always satisfied by pseudo-Anosov flow or pseudo-Anosov flow case, then we can reconstruct a premanifold with the flow so that the action on the bifoliated plane is conjugate to the action on the orbit space. So that's the most recent one. So if you actually think about this in the sketch I gave you about my work with Hongtaek and Pyongno, so we went through the loom space and constructed frame manifold using Floymer and Segerman. But also this action on the downstairs is already a very good action on the bifoliated plane. And it seems every condition I need to construct frame manifold is already satisfied here. I didn't write that down, but maybe we can use this to construct a frame manifold with flow from that picture there. Anyway, so because of the time, yeah. Thank you very much.